Advanced biomaterials are in demand in a variety of medical applications due, among other things, to their non-toxicity. In a Finnish research program, wood-based optical fibers are being explored for potential use, for example, inside the body.
They probably can't replace the classic optical fibers, which have a very small attenuation and you can transmit the signal for tens of kilometers. But there are lots of small-scale applications, for example, in a car, in automotive industry in general, and also in biotechnical applications to mediate or sensing information from the tissues to outside world. So there one doesn't need to have tens of kilometers signal transmittance, but perhaps this length, for example, to convey, for example, signals from the tissue beneath the skin to some sensors.
They are also being used for biomedical application, like such as localized laser surgery. So that means you don't have to introduce some special surgical device. One of the biggest problems in the glass optical fiber is that they are brittle, and they are brittle at the same time they will damage the cells.
Optical fibers made from cellulose have certain advantages over optical fibers made from other materials, such as glass.
One benefit of cellulose is that it's very easy to chemical modify, so we can make totally new type optical materials that are not possible to do with synthetic materials.
We can spin these fibers at room temperature, and we can spin the fiber from 4 degrees up to 37 degrees. And that is the limit for many of the biological molecules if you want to incorporate inside the fiber, if you are looking for more advanced therapeutic applications, which is not possible in polymer optical fibers, just because you have to spin at 180 degrees Celsius, 200 degrees Celsius.
We can make very flexible and soft fibers out of it. It's actually really tough. You can stretch it, it doesn't break. You can also bend and twist it. It doesn't break either.
At the same time, it has a very good refractive index that is very close to the polymer optical fibers. And if you can tune it just by changing the chemical groups or functional group. It has very limited scattering, so that is rather unique.
The optical fiber primarily consists of two parts, the core and the shell. The retention of light in the fiber is based on the total reflection of light, with light coming from an optically denser material to an optically sparser material. These soft wood-based optical fibers offer new possibilities in the laser treatment of tumors and in different internal sensors, such as those used in brain research.